So again, nice to meet you, everyone. I have an outline because it's a long talk. It's good, I have the right. I will start by, in a few words, telling you who am I, what is GI, and what is Magpie. So what is the tutorial about? And then we will have mostly 3/3 of the tutorial. 1/3 which will be very generic because I'm not sure how much you are really good with GI in general, and that will be in the lens of Magpie to tell you both how I see GI and how GI is seen through the tool Magpie. The second part will be much more focused on the technical parts of how it works, and the last third, Magpie in practice, will be how you can use it to do stuff, actually. So I'm Aymeric Blot. I'm here as both a lecturer at the University of Rennes and research fellow at ICSE. You might know the diverse team at ICSE or at other events. And I'm here specifically because in the last few years, I've been developing Magpie. And before that, I've contributed to the second version of Piggy. And I kind of like to write tools. And during my PhD, before my PhD, I developed MOParamI-LS, which was a tool for automatic algorithm configuration and automatic design of algorithms. That will be relevant sometime in the future, in some slides at the end. So what is genetic improvement of software? Because if you just type genetic improvement into Google Scholar, you get a lot of biological stuff. So we are genetic improvement of software. Basically, you're taking software as it is right now. You apply some kind of meta-evolution, and you get an improved software. You can use that to improve functional property of software. You might have earned automatic program repair, which is the right avenue for functional improvement of software, but also improvement of non-functional properties of software, mostly execution time, but also memory consumption, energy usage, solution quality, a lot more. But yeah, mostly those. Mostly execution time. We wish we could do energy and memory better. But yeah, genetic improvement is all of that. On Magpie is a framework which is not exactly made to do GI. I like to think it as a tool, not a GI tool, but a tool that enables GI. If you read the paper on arXiv, you can read that it kind of stands for Machine Automated General Performance Improvement of Evolution of Software. If you want to add an S of Magpie, doesn't work that much, doesn't really care. We will get that on the second part of the tutorial. It's basically a tool that enables a lot of things, including GI. And the main point is it's made to be very easily usable for developer, for researcher. If you want to do stuff and do research, I think you can use quite easily Magpie to write papers, and also for developers as a user-friendly kind of tool. It should be really easy to use on new software, on new things right out of the box. It's still a little bit different of genetic improvement, because I like to think it as you take a model, you apply meta learning, and you get a model, not really software, but yeah, in the end, it's just software, you model it, you improve it, and you get a software and improvement. Brief history of Magpie, because it's not a brand new tool. It's built on Piggy. And if you look at the name on the bottom of the slides, you can see the name of Gabin, which is co-organizing this workshop, and the name of Shin, who I saw on, who gives the tutorial this morning. I definitely won't be there without their work on Piggy first. Yeah, Piggy still exists, but yeah, Magpie is built on top of it. So right now, the first part would be much more theoretical on how we can represent software, how we can model it, on how Magpie uses that space to find improved variants. So if we look at just what GI can do is we want to have a software which is efficient, and the natural idea is it's just program synthesis. You start from nothing and you want a software, and the search space for that is just the space of all possible software. It's kind of a large space. It has a natural representation, just the model you use to model software, but it's kind of hard. If you start from really nothing, then the search space grows really quickly. It's infinite, really hard to navigate. It's definitely not 2D, but I think you can get the idea. If you start from nothing, then you get just one element and two elements. And if you want a software which works, it will be very far from the origin. On which works efficiently, it will be very hard to find in that space, which is why we don't consider that space. We consider the space of genetic improvement, where we do not start from nothing, from scratch, from program synthesis. We start from something that already exists. It does also have a natural representation, which is simply the sequence of transformations that we want to apply to that existing software. It's still infinite. It's still hard to navigate. It's a little bit less expressive because it doesn't contain every software of the world, but it contains all the software we are interested in, which is the variant of the original software. And the key point is we hope that the improved variants that we search, that we are looking for, is really close to the existing one. So we go from a very large search space which contains everything to one that specifically is centered around the original one, the reference one. And we will see that that small subspace contains a lot of interesting things. I think I've been working on software engineering for 5 or 6 years. I still don't know what is software. And I'm of the opinion that it's not that an easy question. So that's my vision of software. To me, software is the description of something that you will ultimately be able to execute. You can say that your software is an artifact, a binary, and you just have to execute it on that software. You can say that your software is the source code, and you need to compile it, and you can execute it later. You can go one more step back and say you have a design space, a model space from which you can derive your source code, and then from data, environments, configuration, dependencies, you get your artifact. Then that artifact you can use a test suite, again, data, environment, configuration, and then execute it. The right thing is we can actually use GI on all of that. Mostly we have been using GI on source code. There have been some work on binary. There have been some work on data, on test suite. We don't really need to know where does really software start or software ends. What we really know is we have something that we can modify, and we can tell in some way if it's good or not, so that we can improve it. And that's the vision I have for Magpie is we just need to take a model of whatever stuff in that pipeline, improve that model, go back to that pipeline, finish it, execute it, and see if we improved or not. So to Magpie, we don't really need to care what software really is. What we do care is that the user specify one model or a list of models that we can see internally and improve internally, apply transformation, get a set of transformed model that we can reapply to the original software, and apply to a benchmark suite, or at least get a fitness function, get a way to see if it's better or not. Some terminology, which is kind of important because I use it all over the place, and not everyone uses the same term for the same thing. So to me, a model is just one representation of one specific aspect of the target software. It can be a source code. It can be a list of lines. It can be a tree. You can say that it's binary. and you are looking at specific bytes or whatever. It's just you take one part of the pipeline, one thing, and you represent it. A variant is a list of model. It's whatever you took as abstraction from your original software. An edit will be the description of a transformation, not the transformation itself. It will be, for example, take that line 2 and insert it after line 7. That would be a description of something that we will do. And a patch will be a list of edits. So a list of description of what we need to do, what we need to apply to the original software. And to finish that first part, how does that search work in practice? So we need to start with an original software that we will use as reference. We will need to choose some part to abstract. For example, one specific file, one configuration file, something for which we will apply evolution. And evolution will be generating a new transformation or removing a transformation for regularization. Apply that transformation, apply that list of transformation to get a new software, test it, see if it's better or not, and continue that until the end. At the end, we have the best version of what we could evolve. That's just one single search. We can try to do a lot more. We can, for example, do a second search for generalization. So do the first search on a set of training data, get an improved software on that training data, and then try it again on another set of data to see if it still works, if we have learned something useful or not. We can try to minimize patch size, again, on the same or different set of data. And something we definitely want to do is manually access the semantics because, yeah, we can't, I don't think we can really trust the AI to really do something that makes sense because we just give it syntax. It makes syntactic transformation. It doesn't explain anything. We still need a human in the loop to say, you are doing something right, or you break it completely, or you're just abusing your fitness function to do something else while giving us a good score. On to the eyes of Magpie, some of the components will be needed to be provided by the user. That would be the reference software at the very beginning, the benchmark that will be used to get the fitness function. Magpie will provide models and search processes, will provide transformations. So the user will need to choose from the set of what is available or to provide new variants of those. And choose the performance indicators that will be used to get the fitness from the evaluation. And everything else is automated by Magpie. And really to finish this section, why does it really work? We usually give two explanations. So the first two hypotheses, one comes from mutation testing. It's the competent programmer hypothesis, which is that someone who knows how to write software will write something which will be close to a very good software. So that way, our subspace on the reference software is a good subspace to consider. The second one came from automated program repair. It's the plastic surgery hypothesis. It's basically during the development of software, most of the transformations that the software sees are from snippets that already exist from the software. And the second part is kind of important, is that those snippets can be efficiently found or exploited. So you can actually find the code that you need from your reference software to apply it to a different place on improved software. I don't really think that these two hypotheses are enough to really understand why it works. I would have one more observation, which is that the software is not unique in the way that you can do a lot of things and get something which is strictly equivalent. You can add a lot of useless lines to your program, so you can modify it in a lot of ways that doesn't really mean anything. And as you move in the subspace, you will still see the same thing. if there is a good transformation that is available from the very first original software, you can do a few moves and it will still be there. Your fix will still be there even if you move. It will still be at the same distance how many equivalent or neutral move you make in your subspace. So you don't really lose anything. And yes, there are infinitely many software equivalent to the reference one, but there are also infinitely that are equivalent to the one which is improved. That's the one you are looking for. Yeah.
Why correct?
Because the landscape that you see at the very beginning, you also see a copy of it while you move. It's not really the best term, but I think it works. It's really that most of the original landscape, you see copies as you move. Something which makes your program crash at the very first move, it will still make your program crash after 3, 4, 10 moves, and your fix will still be there after 10 moves. So that was for the first more theoretical part. I'm on time. The second part will be more technical on how Magpie works, on third part on how to actually use it. So Magpie, in a nutshell, it's a modular Python framework. So the idea is that every part of it, you can change it, and it won't really affect the other part. You can change which transformation you use. We can change which source process you want to use, a local search, genetic programming, search, some kind of new search. It won't affect anything else. You can change the target software, and everything should still work. And yeah, the two pet peeves are it should be easy to use for research, and it should be easy to use it at all. Motivation are multiples. I like free software, free as free and free as lib. So it's a very open MIT license. It's on GitHub. You can download it right now. It's very small sized. I tend to not very like what I code, so I change it a lot. Lately, I've been adding a lot of user-friendly stuff, so the size went up for 4,000 lines. But we will see that it's fully separated well into packages, so it should be easy enough to read if you need to. And it packs many functionalities. And it is made to be both multipurpose and reusable. So you can use it for both functional properties and non-functional properties. And it really uses scenario files. So we can just write the scenario files, give it to Magpie, and reuse that, or just change a part of the scenario that you want, have a different file, give it to Magpie to do whatever you want. What would you get if you either look at the GitHub page or if you download it? It's one big file that I reorganized not that long ago. First thing is documentation. If you don't know d@axis, it's a very nice way to structure documentation in tutorials, how-tos, explanations, and reference. I'm not saying that Magpie has good documentation, but I will work so that documentation improves, and I think it's a very good way. And if you have project on your own, then I really recommend you that way of structuring documentation, because I really think that it's really nice. Magpie has a Magpie subfolder. So one is the Git, and the other one is where all the code lives. And that one is self-contained. You can copy that and it will work. It is separated in a few packages. Core that might be subdivided in the future, which include best classes on all the way to handle configurations. One for models with 4 types of model. We will see that later. Models are between 100 lines of code for the smallest on, I think, 600. That's the one part which is hard to do. Algorithms we have multiple local search algorithms, multiple GP variants, algorithms for validation, algorithms to do ablation analysis. It's kind of a compact way of representing them. So there are at least 7 algorithms. So 100 lines of code is kind of easy to read if you want to write your own variants. Binary is just entry points. It's not really relevant. There are some scripts also. And some things that I did not know before, a main file that we will use to just say Python Magpie and to execute a full directory rather than having to deal with the individual entry points. It also ships with examples. So in the example folder, we have a lot of different examples. And for each of one, scenario files are in a separate subfolder. It's not really the best thing. Right now, I think it's not the worst, and also some tests. What would Magpie look like if you want to use it? There is 2 ways, because the only 2 things that you need is your software in orange right there, and the Magpie subfolder, so the one that contains the executable main.py. So you can either have a copy of your software in the main Magpie repository, or you can just drop Magpie above the root of your software. Both will work. We don't need the test, the example, or the doc for Magpie to work. It just self-contained into one single folder. You will need to provide a scenario file that we will see in the next slide. And the rest is just automatically generated. Magpie work will be where Magpie will copy your software to apply transformation, compile it, run it. On Magpie logs will be where you will find a copy of everything you will see on the screen and a little bit more. And if it is successful, you will have a patch file, a diff file, so that will be easy to look at the result and reuse them. And in practice, we will need to just use Python 3 Magpie, so the folder, and it will work. The name of the entry points that you want, for example, Python 3 Magpie local search, and then give it a scenario file. What does the scenario file look like? So basically, it's what you need to specify to run Magpie. It's a simple INI file from Windows, but it works it's just the formatting. So we can see here one section, which is software, in which you specify where your software lives, which file or which aspect you want to abstract. So here it's just one single file, which is triangle.rb, because it's a Ruby example. We want to use a repair, and it needs 2 commands to run the benchmark suit. One is bash initbug.sh, and I think we will see that in one of the future slides, on one for test to run the test suite, and it will be sufficient to actually run that scenario. And the search, it doesn't say, because you can apply it for both local search and generic programming, but it specifies that as a repair scenario, we want a fitness function of 0, which is the number of bug or the percentage of bug that came from Piggy, and on the number of steps that you want and the possible transformations that you want to be applied on your model, which is here 3 different lines of transformations, types of transformation on lines. There are 4 types of models in Magpie. One that comes from Piggy, which I think is not that relevant anymore, which is Astor, which is an internal way to represent Python programs. So you can do statement replacement, insertion, deletion with that. And the 3 other is line model, which is a way to represent a file with an array of lines. XML model, which is a tree, and config model, which is an hash map dictionary. For those, we can provide replacement, insertion, deletion for both lines on XML. Magpie provides for nodes also, changing the content of what node and wrapping around the text of the node. Yeah?
It was pointing out that you can mix those mutations and change parameters.
Yeah. Yeah. I will go back to that at the very end. The way which file goes to which model is by default, if the file ends with params, it goes to the parameter file config model. If it ends with XML, it goes to the source ML model. Otherwise, it goes to the line model. You can change that. I think it's pretty self-explanatory with the joker here, the star. But you can have any number of files you want to transform, to evolve. It doesn't have to be all the same model. You can mix and match. You can mix and match also which transformation applies to which file. It should work out of the box as you can expect it to work. So one of the models is XML. So it does represent the IS through source ML, which I will talk in the next slide. It represents the IST of a specific file, but in general, it can represent any tree for any abstractions that you have from your software. Here is what a source code file looks through SourceML. So SourceML is a tool that takes source code files in C, C++, C# or Java. So here is C++, and it outputs an XML file that looks like that, which is basically the original source code with XML tags inserted around everything which might be useful. So it's a very large tree. You can obtain similar XML files for other languages. So for example, Magpie provides a script that does that for Python, because Python can read a Python file, get the IST, and you can get an XML file for that. That's basically what I have to say about XML. It's really great because it encodes the tree as you want it. You can modify it by hand. It encodes a valid tree, so transformation on that valid tree will result on a valid tree most of the time. Semantics allowing it, but it's great. And to get the original software back, you just need to remove the XML tags, and you get your modified software. So that's a slide that I've changed a lot with the time. So to evaluate your software, it goes through a number of steps, which can be 1, 2, 3, 4, or 5. Init is not really an actual step. So the first step init is before even Magpie starts. You can execute some commands to have your software in the state you want. We will have an example in the third section when you start with no software. And in the init step, you just download it and set it up if you want. We need to separate init from setup because there are some stuff you want before the abstraction starts and some stuff afterwards. So init would be, for example, to download your software or to run CMake to get your something. And then evaluation is actually in 4 steps: setup, compile, test, and run. Setup is run only once at the very beginning of the search. And for every variance, we run compile, test, and run. So setup is, for example, to do something that will be applied anyway in every step. So for example, compilation of every file you do not modify. You can have that prophylactic step before the search. So you compile everything, and then that state will be used to compile everything again. So you only modify the difference from your transformation on not compiling everything from scratch every time. And then for every variant, you have a compilation step, a test step, on 1 or multiple run steps, for which you can provide different command line, different timeouts, different size of output you want to allow. to avoid things like having an infinite loop that outputs some stuff in the standard output, because that breaks Python, because it generates a lot of output very, very quickly on, yeah, it's not that keen on your system. So you can kill it before it becomes too large on your memory, just explodes because you have an infinite loop outputting random stuff. And it's divided into compile, test, and run just for the sake of it, because it's easier to provide several commands. You could regroup everything into one single command line, but it's better to see, to get an idea where it broke, if it's a configuration step that did not work properly, or if it broke after the test step, or if you actually had to run it one or multiple times, or when did it break. Magpie will output for every variant how it went. And it can simply crash at the command line level. It can just tells you that it did not return, or it returned with an weird error code. It can say that it took too long on Magpie had to kill that variant if it output too much, or if it wasn't able to parse the output. And success would be in the lens of, was it able to get a fitness value? Not successful in finding something good, just successful in running it without crashing. Yep. Magpie provides several fitness functions. Most of them are related to execution time, and we will see them afterwards. One of them relates to program repair, and there are a few others. The one thing that we want to take from this slide is basically fitness function is something that you read from the output, from either the standard output, the standard error. You need to configure it, but basically it's something that happens after everything is completed successfully, hence the success in the previous slide. We will see the execution times one more in details. For program repair, it currently supports JUnit, PyTest, and Minitest. Basically, it looks at the output to see if it fits something that it already know. So for example, for JUnit, it looks at snippets of text with failures, colon, and a number, on test runs, colon, with a number. It needs both because it's really easy to make the testerness crash, and then you say, hey, 0 failure with 0 test run. And that's not a sign that there is 0 bug. It's just the sign that it did not went well. At the worst, you can just have your software output, Magpie output, and anything, and that will be taken as a fitness function. And I think that's the last slide for the implementation part. We have many entry points. There are 3 ways to actually use them. One that I will recommend, which is a new one, if you already used Magpie before, which is simply to run Python 3, then Magpie, which is a repository, and then the name of the entry points we want, which can be Python 3 Magpie local search, like Magpie local search.py bin.local search. It will find it. You can have your entry point, especially if you want to write your own, if you want to change the experimental protocol, you can move it at the top level, and it will work. You can move from Magpie bin entry point to the top level, and then simply run Python 3 on the name of your script. It will work. And if you're an expert with Python, you know what Python 3-m is. And it's basically how to run a script from within a subdirectory, and you need to replace the forward slashes with dots, not use p. It's complicated, so that's why I do not recommend it. On Python 3 Magpie should be the easiest. You do not need to know anything about Python to just use it. You just need to provide your software, the scenario files with no real Python, and Python 3 Magpie and the name of the entry point. That will be sufficient. Magpie provides 2 entry points for search, for local search and genetic programming. There are variants of local search, variants of genetic programming, but it will do the full evolution loop to get you an improved software if it found one. Then you might want to run Magpie again with a validation algorithm. I think I have a slide later on how to do that with your hands. So I will not be that long on that. But yeah, you want to run Magpie a second time to make sure you have something that actually works. Some other script for showing you actually what is every location that Magpie can see, and utilities to take an XML files and remove the tag to get the original source code back, a script to get from a source code file and an XML with just separate line by line. So you don't really need the line model. You can just use that and use the XML model one. And Python to XML, which is the equivalent of source.ml for Python files. And the part that you are all waiting for, how to use it in practice with first steps and then harder stuff and more complex stuff. We do not really need to go to the very end, but I think I will have more than enough time. So Magpie in practice, so it's available on GitHub. You can simply clone it and go to the repository, just clone, and run Python 3 Magpie and something. So local search, then scenario, and one of the examples, and it will work. It should work. It will work. And that's the one example that I will use in the next few slides. So if you want to go along, you can. There is that specific example on the very page, on the very landing page of github.com, Blot Magpie. So you will have that one thing to go along. So it's an example which is triangle C, which is one of the most used basic example of genetic improvement. So it's on Magpie, it's on the example folder on triangle C, where you can see a program which is both fast and without fault, because it's easier to just have one version of the software. It does have a triangle C file, a triangle H file, which contains the header and the code of one single function that takes the three lengths. That takes three lengths and tells you if it's a triangle or not, and if it's which kind of triangle it is. A make file to just compile it, and a run triangle.c and test triangle.c. Test triangle is simply a test suite, and run triangle is just code that use the one function in triangle C that we will use to look at how fast it goes, how much time it takes. In orange, there is one more file, which is init slow, which will introduce a bug, introduce a way to make that file slower, and that we want to fix. On the Magpie specific file, you will have the scenario file, scenario slow.txt, and three more files, a diff for triangle.c, a diff for triangle.h to seed the fault, and an XML file so that you don't have to download source.ml, but you can regenerate it yourself. In the scenario file, you will see that we will do one thing at the very beginning, which is execute init slow.sh, which will simply apply the two diffs and put the XML files just one folder before. Above, there will be no setup step. Compilation will just be a call to make, and test and run would just be calling the test suite and calling the payload. The bug, you can see it right now. It's simply adding one more function, which is delay. Yeah, I must acknowledge that the C file, the C version of the triangle program is written actually by Bill. So I did not have to look at how to make that function in C. That that's right. So that bug is adding that function and calling it in the main function. So it adds one delay of 0.001 second. So it's very slightly slower. The scenario, we need to see which software we want to improve. So example, triangle C. The one target file, which is triangle.c.xml, so it will use the XML model. We want to improve execution time, and then the three commands from 2 slides before. Init flow to seed the fault. Compilation is just make on for both the test suite and the payload. Test is just running the test suite. Run is running the run command. And we will kill anything that takes more than 1 second to run. Search, we will do either 100 steps of local search or 60 seconds. We will use replacement, insertion of deletion of statement. And if you run it, what you will actually see is Magpie running. There is something before that that you don't see that will appear in your log file is the full configuration. In case something goes wrong and you want to email me what is the issue, so I can see everything that is recorded. Then you will see a few steps of warm-up, which is used to make sure that the fitness function is reliable, because usually the very first execution is weird. It's either faster or much slower than any subsequent execution. So by default, it will do it 3 times and use the last one as reference. You can change that for the mean, the median, the number of warm-up. You can change everything. And then it will start the local search, because in the command line at the very top, we told Magpie that we wanted to run the local search. You can see that the first variant did not pass the test suite, so it has no fitness, but it had one transformation. The second one was successful and was slightly faster, so 0.08 seconds, because it did not output the full precision, but it's 96% of the original execution time, with a star saying that it's the best fitness that it's seen so far. Third one was successful and slightly improving it, but it's mostly noise. 4, 5 was also successful. 6, 7 were issue in the test suite, so we break something in the source code. 8 was successful, but much slower. I killed it. And you can see that just before I killed it with caret C, it found something which ran in not 0 seconds, but very close to 0 seconds, so 4% of the original one. So it found something in 2 edits that solved the bug. Magpie ends because I killed it. It tells you why it ends, why it ended, be it either a keyboard interruption, whether it ran out of time or ran out of steps. It will give you where it puts the log file, the patch and diff file. If it found something interesting, it will recall you the reference fitness and the best fitness. So here 0.08 seconds and 0 seconds. It will give you the best patch in the internal representation of Magpie. And it will give you a diff that we can look at right now, which is basically on the line in the delay function that actually calls the no sleep. It just deleted that. And the second part of the patch is adding another return after a return. So it's a neutral transformation that did not change anything, but was present at the end of the search. What can you do with such a patch? So we have two edits. You can look at it because it's beautiful. So you can change in the original command line Python 3 local sort by Python 3 show patch and give it, you need to give it the scenario because otherwise it wouldn't know which reference software to consider. You give it the patch, you can give it the file directly. So you can copy paste from the output you have. You can give it a file from the Python log directory. You can give it the patch directly on the command line. And it will just, without re-executing anything, it will just take the original software, abstract the model, apply the transformation, and show you the diff again without executing it. You can give it the keep option to actually keep the modified software because it does not do it automatically to make sure it does not fill your disk with a lot of crap. You can revalidate it, be it on the very same scenario, or for example, if you might want to change the run command to run it on something different, possibly much longer, to keep a short run command for the actual search when it applied many times, on a longer one to verify it. And then you use Magpie revalidate patch with the scenario on the patch. You can try to minify the size of the patch. So again, Python 3 Magpie minify patch, and that will start a 3-step local search, which is kind of usual for GI. It will first try every edit independently. It will then try to rebuild a new patch with individual edits. And both if that succeeded or not, it then will try to remove individually every patch to get you the minimal patch that gets the best fitness. And one last entry point is ablation analysis. I don't have a specific slide on it. What it will do, it will take a patch and it will give you the order in which the patch are useful. So for example, if you have 10 transformation, it can tell you that which transformation takes you 80% of your improvement, which one gets you the 10% more, which one just is noise and doesn't change anything or change 0.1%. So it would be kept by the minification because it's useful, 0.1%, but it will give you the individual contribution of each individual edit. You can change the fitness function. So I said that for execution time, we add time, POSIX time, perf time, and perf instruction. So in most examples, when you use Magpie, it will just use time, which is a bad one. It's the one from Python, which just look at the clock, execute the command, and look at the clock. It's pretty noisy, but it's precise because Python has a good clock. But it will get you the noise from executing the command, from process handling in Python. But it comes from free because it comes from Python. So that will always work. You might want to use user bin time, which is available under most Unix system. And so Magpie provides a POSIX interface to that. So if you change your run command from run triangle to user bin time -p for POSIX and then run triangle, you will get real user on system on some time on your standard error. And by telling in the scenario file that the fitness is POSIX time, then Magpie will look at the standard error to look at the real system user time to get that time. The issue is that user bin time is something like 0.1 second precise, which is really bad. The next one is perf, if you use Linux in particular. Perf is a kernel tool that does a lot of things, one being recording of statistic for executions. It is a lot less noisy than the two others. It's only available on Linux, and you can, but if you are on Linux, it will give you a very good clock time on what the software used. So you will need to change your run command from just run triangle to perf stat run triangle. You can change that line to tell perf to only get the time, but that's the minimal things you need to do. And it will give you the actual time. But if you are, for example, root on your machine, or if your system administrator enabled that perf add the statistics on hardware counters, you can actually get perf to give you the number of CPU instructions that were triggered during your execution. And that is almost deterministic because your CPU is not deterministic. It will get you 99.99% of the way. So it will be incredibly precise. It will be very good, but you need to either be root on your machine to enable it yourself or have your system administrator to write the right configuration, the right option in configuration so that you get that hardware counter for CPU instructions. Perf give you a lot of other things. I think Bill played with a few of them with cache invalidations, number of cache invalidations, or context switches. It gives you a lot of things that you can use to get better software. You can change a lot more things in your scenario files. If you're doing research, one thing that you are very interested in is reproducibility, which is not very great when you are looking at execution time because it's very noisy. But you can put the random seed to get a somewhat similar execution. If your fitness function is deterministic, then you will get the exact same thing, hopefully. That's something that will be printed in your log file. Even if you did not specify it, it will give you a random seed. It will write it on your log files. You can repeat your experiment afterwards. You can change your warm-up to have more warm-up evaluations or fewer. Or if you want to use the last one, the mean one, the max one, mean, median. That's why the framework is so big with 4,000 lines because I need to check all those options. And for the length of the search, you can configure it how many steps you want to give it, how much time it might use. And if you already know the target fitness, so for example, for repair, you want to have 0 bug, so it's easy. But if you want to have the software which is twice as fast, you can just use 0.5 as, or no, not a percentage. You can write the fitness that you want, and Magpie will stop when it reaches that. So that was the easy example. So if you want to do something more complex, let's consider Minisat. Minisat is almost in the example folder. So if you go to Magpie example Minisat, you will see not Minisat. You will see init.sh, compile.sh, test.sh, run.sh, basically no source code. Because in init.sh, what is specified is how to download Minisat, how to cache it, so it downloads it only once. And it will extract the source code from internet to that folder. It will insert solver.cc.xml at the right place, again, so that you don't have to have sourceml installed to run that example, but you can regenerate that yourself. Setup and compile will use compile.sh. Setup as a prophylactic step, so it will just run make to compile everything that you will not modify, and compile test run are run every time, so that the make that you run in compile will only recompile the file you touched. Test run Minisat on small instances, runs Minisat on much larger instances. So the instances are in data, and that's basically stat formulas that Minisat needs to say whether they are satisfiable or unsatisfiable. For the test script, we just have a list of 10 or 20 or 50, I don't know, really simple formulas to make sure that it goes through that 50 test cases very quickly and give you the right stat or unsat. On run, we just use much larger instances. And yeah, there is a minisat.config because you can specify a lot of things in the compilation line, no, on the CLI of Minisat. So at execution time, you can change many options that change how the software works. And that we will want to optimize right now. Scenario files, the only thing that we care about is the target files, which will be minisat.params, which will be the file just below, and possible edit, which will be param settings. So by default, the file end with params, it goes through the configuration files model. And the parameter files is just a way to describe what you can put in the command line to run minisat. So it has a few parameters. For example, core tolerance, which will be used in the command line as dash core tolerance equals a value. And yeah, so it specifies all the things that you can put on the command line. That file is really easy to understand if you try to read it. It has some magic constants. So for example, prefix or glue to actually write the command line. Timing, which will be when, at which command will be this configuration file used. So for minisat, it's only at runtime, but you can use the same to, for example, change the parameter of your compiler. You can have a configuration file for the compile command. And it supports categorical parameters. So the name of your parameters and whatever set of values, which can be any values or true or false or none. There are constants to set up how they are exactly used in the command line. It supports numerical parameters, either continuous parameters, exponential ones, discrete ones, geometric ones. It will handle a few strange things, for example, that line with -1 billion and 1 billion. It will understand it as two geometric distributions from both sides of the row, because uniform will only get you very large value at both ends, but you will actually want to explore the full geometric distribution. It also supports conditional parameters, forbidden combinations on a few nice things, which I don't think I have the time to explain why they are really nice, but invisible parameters or invisible suffix, they're quite nice if you actually want to write a configuration file, can find them useful, but yeah, supported. So that minisat scenario, the run command is simply run the run.sh file, which looked like that. It's a file that run minisat many times. And that's the one thing that we want the execution time of. So if that file takes a very long time to execute, it's bad. If you can try to reduce that, it gets better. But it needs to go through that one file in its entirety. You can add batch processing. So instead of just run sh, you can have a run sh that doesn't know which instance to run it on, but simply give it a list of instances. For example, here you give it 2 bags of 1 bag of sat instance, 1 bag of unsat instance. You tell it, I want to run your run command 4 times, and it will take at random 2 sat instance, 2 unsat instance, run them, and give you the execution time. It will draw them only once at the very beginning of the search, so that you can actually compare your run. But every time, because of the random seed, every time you run it again with a different random seed, it will take different instances from your instance bag. So you can add that. You can combine models. So if you want to, for example, modify the source code and modify your configuration file and your compiler configuration and something else, you simply have to specify it to Magpie. So you have a list of target file. Each of them will be associated with a different model, which will give you the Magpie variant. And you just need to specify which edit it has the right to use. And the other operation is Magpie first pick one edit at random, then try to find one model that it can apply the transformation on, and then it will generate everything. So param setting it will, for example, if it picks param setting, it can only be applied on many stat.params. So it will try to modify the value of one parameter in that configuration file. But if you add several, it will first pick the type of edit, then on which model to apply it. I arrive at the end of the presentation with complex stuff. So XML3, we can, I showed you before that in the source.ml file, the tree was really large with a lot of things that might be useful. So every little thing has an XML tag associated to it, and you might not need everything. But you can tell Magpie to apply transformation to whatever type of node you want. So by default, it has, for example, source.ml statement deletion, which is just an abstract node deletion that only apply to statement types of node. And you can, with these two lines, create any new types of XML node deletions. You just need to specify which type of node it applies to. Same for insertion or setting or wrapping of text. Insertion, it needs to know the type of the node and the type of the block in which it appears. So the parent. For settings, you need the type of the node on the different value it can take. For example, you can specify, Magpie provides source.ml numeric setting that will target any node that is called number and replace it with either 0, -1, or 1. And wrapping, it will again take something which is a number and keep the text, but wrap it with parentheses with, for example, +1, -1, or divided by 2, so that you have your source code, you run it through source.ml, you have an XML tree with just number, any number that is natively in your source code, and the end of the tag. And Magpie will just take that number and then wrap with parentheses and add 1 or remove 1. If you want to provide your own code, you can do that very easily with simply adding import equal your file in your scenario file. And you can, for example, write there, so import Magpie because that's a library. Those are two examples of two new transformations. One is the replacement of any node which is called type. And the second one is text setting. So it will take a node which is a type and replace the content of the time, more than enough time, with either float or double or int. You will need to tell Magpie that this class exists because I'm not that good in Python. So you need to do that explicitly so that in any entry point, it will be able to look at any patch and see that it's a type setting and then get the right class. And then you can use it directly in your scenario file. You can do that for transformation. You can do that for models, for algorithms, for the experimental protocol, which by default is just running the search and give you the report. So you can write your own Python code to modify Magpie and then do that in a scenario-based kind of way. I still have more slides. So I think that's the last one for the tutorial part. Because the XML tree can be very large, it might be useful to reduce its size. And Magpie can process the tree. So for example, in this example, in this case, it will rename any tag which is named break, continue, declaration statement, do, expression statement for, and it will rename that for statement, so that with a statement replacement, it will take any node which is break, continue, declaration, and replace it with any other statement node. Focus, it will just delete everything which is not a block of our statement, which you need statement for replacement and deletions. You need block for insertions too. Internodes, it will actually create the location for insertion because otherwise it's kind of messy the way that it can only be after a node or before a node. Magpie will just create the location everywhere it is interesting. It can process a few things. So for example, in C, you have syntax that allows you to just have a single line if or for you can imagine that if you delete that line, it takes the next one as the body of your if or for, which can mess your software pretty hard. So Magpie will just add explicit curly braces to keep the same tree, but you can disable it. For literal or operators, it provides a few things to make sure that the output of sourceML is really usable. And you can specify that for sourceML or param config either globally or as a model by model basis. So you can say that in this file, I want to run anything, but not in the other. You can do that. And I think that's the last slide in the Magpie practice. And I have a little time to finish with future direction on challenges. So I think that's 2 slides. So what do I want to do myself with Magpie in the future? The next thing I think is performance indicators. We have mostly execution time on repair, and that would be really nice to have some out-of-the-box indicators for memory or energy. Yeah.
User bin time dash you're using user bin time for the
yeah, but I don't think that I actually put an indicator to read that. But yeah. But yeah, perf can give you things with memory. User bin time can give you things over memory. It would be nice to have scenarios which we can apply very easily to new software to improve memory, for example, because it's really hard to get multi-objective optimization working. Right now, you will need to write Python stuff to actually make your multi-objective things. It would be really nice to be able to say, I want both time and memory, and it will read both and give you information on both. I really want to have support for tree-sitter. If you do not know tree-sitter, it's a parser generator for any language you want that would be able to support everything on Earth for free. It's not that easy to set up. Magpie does have some support for, it has mostly support for Linux, but it should work on Windows, but I did not really test it. It might have support for container or cluster or running Magpie in cluster. It would be nice to have that better. And for housekeeping, I still have documentation to write, tutorial to write, so that will come in the future. And my last slide is the wish list, which can be a jumpstart for the discussion for the last panel. For a tooling perspective, what I think Magpie likes or GI tools likes in general is visualization on interactivity. I would really like to see what Magpie does, which variant it tries to understand something, or in the other way, to look at the model to see it try to modify its stuff in that file and that file on to be able to understand something, or to be able to explain or to tell Magpie that that part is not interesting, so stop actually transforming it, or that part is better. So some kind of interactivity. And for research perspective, so not, at least not Magpie, fault localization is something that exists for automatic program repair. We don't use it in Magpie or any GI tool, any general GI tool. That would be very nice to have. Semantic search guidance, because transformation are generated at random, and that kind of bad. I think we can do better. Performance prediction, because performance is the one thing that takes all the time of GI. It would be nice to see it's really close, that this previous variant that we executed, maybe we don't need to execute it again. On explanation in 2 ways. So Magpie to the user to explain why it found something, on what did work and what did not work, to have an actual semantic report. And in the other way, an easy way for the user to tell Magpie that that function is important. That function, you need to consider a little bit more, this one a little bit less. You can do that, but it's very cumbersome to set up. And that was my last slide. So Magpie, it works. You can run right now. Please do not hesitate to send me an email if something does not works out of the box, or if you want to do something, I can walk you through or explain it how I can see it, help you with doing either research or just using it. That would be very keen to do that.
All right, thank you, Aymeric, for your talk. We have 2 minutes left before the next talk. So if you have any quick questions, feel free to ask.
Not really true ASD. Not even sure it's like vibrationally.
So I think it would be very nice to have it at the very start of the search to get a model, because it supports trees that are not exactly valid. So for example, if you are writing some code, it can detect that you are writing an if on close the right part of the ICSE at the right part, at the right places. I don't think using tree-sitter is really interesting, but using it to get the initial tree would be very nice. I think it outputs for each node the character at which the node starts and the node ends, and that will be sufficient for Magpie to just say that is one type of node, and I can replace it with any other type of node. It's just a way to get the initial tree. It's not that easy to set up because I think you have to download the different grammars. You can't really trust anything. You don't know if it has been updated or not. But it would be, I think, a very good alternative to SourceML or to write a visitor pattern for every language in the world. If you have something that just takes curly braces as structure, I'm pretty sure there is a tree-sitter grammar for that, and it will give you the tree with all your curly braces. Even if it's broken, it will be able to get a valid, almost valid tree from that.
All right. If there aren't any questions, sorry.
So, question for Aymeric. So you mentioned Linux a lot. And does it run on Macs? Does it run under Windows?
It's Python only. It does not have any dependencies. So it should be able to run mostly. There are a few things that are Linux specific, but I don't know whether they should work on Mac, because Mac is Unix. They might work on Windows, but I do not have either a Windows machine or a Mac machine. The one thing I'm really worried about is the process support in Windows. It does not handle processes the same way as Linux, when you can have a process group and you can clean everything. I'm not exactly sure in Windows when you try to kill it if it actually kills it, which might be an issue when your whole setup is just running things, running random software and killing it if it just doesn't work. I hope it does work and it does kill everything. It's something that should work on Linux. It should not leave any zombies or rogue processes. It has been known to happen. Should not be bugged anymore, but it's really something that is critical. So that's why, for example, container supports or better cluster support to make sure that it's running in an environment that you can really be sure it's not destructive and won't kills your OS or kills your Python process, because your subprocess is generating a lot of output and it just breaks your RAM and swap and everything broke because you have a print in an infinite loop, and in 0.3 seconds it just filled your everything.